always interesting when somebody invites you and says, could I have 100 words or something, and you forget to write back to them. So unfortunately you then pay the price when they do their own e-search and find out about you. All right, so welcome everyone, and thank you very much for coming on such a cold night. I've got to switch. Actually, I could give this entire slide. That could be my lecture. Dave, you forgot to actually do this. And so, as part of the university, we always acknowledge that we're on the lands of the Wurundjeri people, being custodians of this land for thousands of years, and acknowledge and pay our respects to their elders past and present. It's just a little bit of respect that we always do at the start of any public event. All right, now, Dave, I'll learn about this. The escape key doesn't work on this computer, so there's no escape, but there's somebody else who decided it's a feature. All right, so it's, let's see if we can get the lighting. Can you guys see clearly at the back under those lights? Cool, okay, I've got a couple of hands at the back, so somebody's awake at the back. Anyone who's been to one of my lectures knows that they're terribly boring, and I tend to grab a book and read it. And so I'm going to tell you a story, and it begins a long, long time ago. And the story is me and what my aspirations were, because there was none of those things that David said. I was going to be an astronaut. And so I think it's fantastic when David said, oh, could you come and give us a lecture on, you know, the moon and everything else like that? And so that was me. That was Rog. That was a dream. Sometimes dreams come true. I don't think that one did. Anyway, so instead, I ended up working somewhere on this scale. Now, progressively during tonight, I think I will probably touch a nerve with everybody about a discipline that you might have a particular interest. So I'm going to try to be all-inclusive. So if you feel left out, please let me know. Now, David's reassured me that everyone's very shy about responding. So could I just see whether you're the type of people who should be at this section? Put your hand up if you love or hate physics. Love or hate physics. Okay, so I've got a feeling for the type of audience we're dealing with. About 3/4 of the audience put their hand up, so that tells me something about my delivery. Anyway, so where would I work on this? Well, maybe I would have to choose, if I'm really going to go to Earth and space on the extreme, or maybe I'd end up fundamentally right at the other extreme, working on logic or formal sciences, or somewhere in between. And of course, I looked up the big book, and I started at A for accounting and aeronautical engineers, and I went through the career guide. I thought, I'm never going to get there. And then I realized that there was one discipline where I was going to go, and it was right to the top, and it was physics. Now, of course, there were all these other disciplines, but I told you I'm going to annoy somebody. I've seen the reaction already. How dare you put physics at the top? What are you doing in a physics lecture? Like, you know, what did you expect, right? And, okay, so I realized that that wasn't the truth, that physics really belonged at the bottom. It's the foundations of a lot of work, and that's what we do. We lay concrete, apparently, or something like that, for the other sciences. And that's not quite how I see physics. And although I did do a PhD in nuclear physics, and my PhD supervisor is somewhere here in the audience, yeah, there he is. Max Thompson's here. He's going to feature later on in tonight's lecture on a very important publication of his that had nothing to do with any of the physics we did, but apparently it's woven into tonight's lecture. And I view this more holistically, the circle of life. This is what physics really offered me the opportunity, and physics offered me the opportunity. Notice it's all about me. None of that work that David talked about involved any team. So I was just one of 52,000 people working on all those experiments, right? Anyway, and so the language of science, you know? So for the mathematicians in the room, you're our language in physics, and for the chemists, you know, maybe use a bit of physics, you know, and you come right around to the medicos who use the language of biology and biochemistry and all that, and you push around to the psychologists and the philosophers, and then where do you end up? Back at physics. So that's it. That's my view of the world. It just goes around and around in circles, and physics is it, and this is really what explains this Earth. But you were brought here under false pretenses. You were told apparently that what was the title of the lecture that you've come to? Do you remember the title? You've forgotten too. Yeah, me too, I couldn't remember it. Apparently it's oxygen and the moon or something like that. So I guarantee you I will mention the word oxygen, I'll mention the word moon and something or other too, and by then you'll have remembered the title and you felt that it was important. Thanks very much for coming, everybody. This is the modern way of giving lectures. Our Vice Chancellor, right, you missed the whole lecture, I'll start again, right? No, thanks for coming. Yeah. Apparently we're going to give up lecturing because students don't come to lectures anymore because they don't see, you can all watch it on YouTube. So there was tonight's lecture in case you want to go home and watch it. But in the meantime, if you want to hang around, do you want to hang around or do you want me to stop? Hang around, okay, we're a really easy audience. I mean, like, you should try our students, they're all on Facebook. Yeah, right. Okay, so what do I know? Apparently this is the Earth, and here are a few stats I know, and it's only because we've been taught well by the likes of Max and Tony and a few others in this theatre tonight. And apparently it weighs a lot, it's got some gravity. Max got in trouble years ago in the age for actually putting gravity with 10 metres per second squared, you know, because we're trying to make it easy for students, and that was not acceptable. The age here was 9.8, so Max and I worked it out to 7 significant figures for the age building on the second floor where they were and sent them the updated number. Anyway, and then we have an atmosphere and we've got life. Well, we've got some sort of life, certainly around the Australian. If I pick the other view of the Earth, we'd question, you know, like maybe the North American continent, maybe if I consulted someone there too, we'd question what sort of life there is there. All right. Now there's this object, the moon. I promised you we'd mention the moon. Now notice it's not to scale, just for anyone who's worried about this, because it's actually not to scale, but it weighs a little bit less than the Earth, and the gravity's a little bit easier. Apparently you bounce around on the moon. How would I know? I've never been there, right? And last time I looked, apparently there's no life, not life as we know it. We're going to have to define life. And then there's the other part of this story, the trilogy. The sun. Now the sun is pretty heavy. It's much heavier than everything else that we know of, apparently. I'm not sure anyone's gone to weigh it, but would you ever ask yourself, like, all the climate scientists, you know, the climate deniers, you know, what the hell would scientists know about the climate? Yeah, apparently physicists tell you that's what the sun weighs. What do they take us? With sort of a spring scale and go and measure the sun? How do you know these things? They're all apparently the things that you can study in physics, and I guarantee you there's no life as we know it on the sun. I'm pretty confident about that one. I'm not confident about the moon. No argument so far. Everyone's in rapid agreement. All right. This is how my mind is. So if you were expecting that I would start at this end of this table and do demonstration 1, 2, 3, give a bit of a lecture, and 4, 5, and in the order, it's not going to happen that way. It's going to be a bit of a jigsaw puzzle. We're going to put the lecture together and we're going to get more pieces, you know, shedding some light, going from dark, a little bit of light. You see there's some strange pieces up there. Maybe we can find what those pieces are. Then we can finally put the edges around this story. And the story is going to involve the following: the moon, oxygen, and physics, right? Cool, okay. So let me know if I go off topic. All right, okay. All right, so let's talk about life. right? Are we on topic or off topic? What do we need for life? Audience participation. What do we need for life? Somebody told me, I checked it out, money. That's not the answer I want. Hey? Yeah, I know, you're going to go there, you can't go there. What do we need for life? What do we need? Nah, you're falling for this thing. Oh, oxygen or? Water. What a good idea. Right, you have to get me? That's amazing. One day we're going to have an extra button so we can jump to the oxygen slide or the money slide. You know, that'd be really nice, right? Food? No, water's a food. Yeah. No, we got the food. That's the sunlight. So we'll come there. So it's really easy. All organisms, as we know, need water. Do we agree? We're going to do this by consensus tonight. It's the first July lecture that you'll ever have that's driven by consensus. So if we agree gravity is 10 meters per second squared, we'll do it by consensus and we'll change that fundamental statistic, all right? Okay? All life needs water. How do we make water? Well, this is really simple for a physicist because we're alchemists. You know, we just apparently get a bit of hydrogen, 2 hydrogens, 1 oxygen, you call it H2O and you push it together. All right. Whoa. Hang on. There's a little bit of presumption there. So we got no money, we didn't ask for money, so I'm going to ask you a rhetorical question. How do you make hydrogen? Well, with protons, because I'm a nuclear physicist, so I know that apparently. Okay, let's get the philosophers involved. How do you make protons? And so these were the lovely questions that physics, as a young student, allowed me to actually engage in and wonder about. You know, the wonder of physics, and somehow all of this has got to do with it.
Our whole universe was in a hot, dense state that nearly 14
How many people in this audience watch this?
started waiting
That's the very percentage of my lecture. The majority of this audience don't know, but that's the Big Bang Theory, one of the highest grossing shows on TV. Now, if somebody had told us, listen guys, let's make a TV show about a bunch of nerds and make a fortune, no one would have believed us. But anyway, how do you make protons? All you need is a Big Bang. You know, that's right. Just start the universe. Wind back 13.67 billion years ago and kick off the universe. And then you notice, by the way, when you study physics, there's both matter and antimatter. There's a little bit of an asymmetry. This is, by the way, called hand waving. So when physicists do this, it means they're on shaky ground or whatever it is. What the hell would I know? Apparently I studied all of this, right? Do you get me? A little more antimatter in the universe than there is matter. Oh, sorry, matter than antimatter. It doesn't really matter. We might be around the wrong way. Don't know which way it is. How do we make oxygen? Yeah, it's not quite the Big Bang, but thank you. Good try. You'll see in the end, it's a good try. If at first you've ever been told a fact, try that is the answer to the next question. We tell our students that all the time. What's 2 plus 2? 4. What's 3 plus 3? 4. Nothing, right? Okay. All right. We just need some sort of oxygen reactor called a star. All right. And so in my studies, I was able to find out a little bit about how from the Big Bang, the temperature is really, really hot and we kick off and we get fusion happening and we get to helium-3 by this complex process. And by the way, there's a little bit of a subtlety there, a little bit of a transgenderification of a proton into a neutron, which magically happens. Now, if you really want to find out about it, the person in the audience, I can't see where he is, the absolute expert's just sitting there 5 rows back from me, he'll put his hand up later. Ask him about that sort of reaction, how a proton can suddenly become a neutron. It's extremely convenient. And then you go one little step further and you suddenly burn helium-3 to helium-3 and you get helium-4 and you get some extra protons. And lo and behold, you almost get there. Like, what are we trying to make? Oxygen. So within a star, you start to burn the hydrogen to make helium, you burn the helium to actually make carbon-12, and you finally get to oxygen. And David and I know that is so not the story. That is so not the story. Graham Sargood, who started the, Graham kicked these off, was it, or the lectures, the Transtop lectures? Tony and Graham. Graham spent his entire life of overseeing students measuring the scandium-45 bottleneck or whatever it was. I can never remember, Dave, that was your area. Where students try to work out how you form the universe. That was before supernova were really, discovered and all those things. Anyway, that's roughly a good enough story for hand waving tonight. Now, talking of hand waving, let's insult the chemist. Many chemists in the room tonight? Okay, feel adequately insulted, because chemists had this great periodic table. Actually, for any chemist's lecture, there is always a periodic table on the side of the wall. They're very proud of it. Maybe not anymore. Maybe the university doesn't allow you to have photos in there. And here were the elements as far as Mendeleev found. We had hydrogen, and the next element we had was lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Got a lot of them. There's a couple missing. But you see, they were chemists, and this is the patterns that they love. 1, 7, 9, 11, 12, 14, 16, 19. Can you spot the pattern? I guess not. It's a very boring answer, but it was Niels Bohr who had to actually come along and actually sort this out later on. And that's yet another lecture, which is not tonight's lecture. But physics very quickly started to try to put some order around this. Now, don't forget, we're trying to simply make oxygen. We made hydrogen, apparently. We had a Big Bang, they made hydrogen. And the Big Bang also makes helium. That's it. Notice, by the way, we're cheating. We're calling this hydrogen 1 and helium 2. You know, with a number of protons in there. And so, as we actually fuse, you know, and burn and, you know, push matter together and together, we can go from hydrogen to helium to lithium, beryllium, boron, nitrogen, oxygen. We can burn this all together. And in fact, we can make those in little low mass stars as they die. And then if we find big exploding stars, we get the CNO cycle that kicks in. And then if we keep going and we get fission happening, we build the entire periodic table all the way up to element 104 or 5. What are we up to nowadays? I don't know. You know, this one goes to element 103. Oh, that was Lawrencerium. I can't remember what comes after that. But there are all these human-induced made. The US military and the Russian military own this corner, I think, down there. That's all of their work down there. And the Iranians aren't allowed to look down there, right? Okay. Anyway, so that's the periodic table as we know it. So if you want to work out how to make anything, let's look at, I think I'll have some, erbium 77. So I'll go and find myself 2 neutron stars, merge them together, a bit like any good corporate bank would do, and off we go. Now, what's this got to do with stars? So stars, now Steve's set up some demos here, so what I'm going to choose to do to make sure I stick to time is I'm going to do my demos towards the end, because I have a really good habit of just getting stuck with the demos and therefore never giving the lecture. So we'll give the demos just towards the end. Anyway, so when you look to the Milky Way, you see stars. And if you look with a telescope and a prism, you can actually see that the Milky Way is made up of mainly hydrogen and helium. And then, nothing like giving a lecture to learn something. It's a little like walking into any lecture theatre in front of your students who've spent the last 3 days learning about it. And I, lo and behold, didn't know oxygen was the 3rd most abundant element in the Milky Way, possibly in the universe too. That came as a real surprise to me. And I wondered about that. And then I looked into it, and it was such a complex story that I can't even tell it to you, but it's an interesting fact. How would we know? How would we know? And it's very, very, very straightforward. Hey, Steve, do you reckon it'll work? Can we go live or not?
Yeah.
Yeah, so Steve has set up some hydrogen, which, if he dulls it out, we've got a hydrogen, is that a hydrogen lamp? Yeah, it's hydrogen lamp. There's that purple look there. And Steve's going to route, what do you want me to do? Anything or not? Dot cam, okay, go to dot cam 2 onto there. And then the lights will automatically change, thank you very much, in this theatre. And then video feed 7. Whoa, oh, beautiful, Steve, whoa. I don't believe we've got a theatre in which we can actually black the lights out. That's very rare. So what Steve set up is a little bit of hydrogen, and he's got a prism. And although you can see the purple glow of the light, Steve, can we run the risk of turning it so people can see the purple glow? Yeah. So there's the glow of that hydrogen lamp, but rather than being a very broad, sorry, I'll get out of your way so you guys can see, rather than being just a broad, reddish purple or whatever, it's a very narrow line. And Steve, unfortunately, I disturbed it for it. Oh, there we go. And if Steve had a telescope with a prism on there and then put his spectrometer on it there and looked at a star, and if he saw that narrow line and measured the wavelength of that narrow line, he'd know exactly there was hydrogen there. What if you had another element, Steve? Do we run that risk or not?
Now we can do it.
You got helium? Show everyone the colour of helium first, yeah. So, well, that looks pretty white. That's a, it's sort of like, a Bunnings, Bunnings white light, soft light for your kitchen. And let's line that up and have a look. Oh, and look at that beautiful pattern. And when our students come to study physics, in both in VCE and in first year, we go to a lot of trouble to actually have them understand these very series that create these patterns of light, the Balmer series, the Lyman series. And by looking at the wavelengths of these, we can identify the elements in stars. And then by looking at subtle changes in their position, we can work out whether the object is actually approaching us or receding us, i.e. the Doppler shift. Thanks, Steve, that's great. Yeah. Do we, you can get me back on. And so, yeah, main computer on center screen, please. Yep, that's it. And in fact, if the demo hadn't worked, here's one I prepared earlier, which would have been, here's the video that apparently this is what we do. But Steve's done it live. And in our lectures, by the way, we pride ourselves in trying to do these demonstrations live so the students see. You can put your hand in front of it. And so there was a hydrogen line that we're looking at. And by the way, you can either look if there's hydrogen burning and emitting, or if there's hydrogen gas between what you're looking at and absorbing the light. Okay, so that's how we know. So the more of the jigsaw puzzle, we're putting this all together, it's going somewhere. All right, so how big or small is the atom? Well, apparently it's pretty small. But how small is it? And so everyone's here tonight. Did anyone want to go to the footy instead? Yeah, all right. So let's actually zoom in on Victoria. There we go, we'll zoom a little bit further and we'll end up at this great spot called the MCG, and this is live cam into the MCG tonight, and you know therefore I'm telling you a lie because there's no game at the MCG tonight. But I want you to imagine the MCG is this size. So that's the MCG, and I'm going to call that an oxygen-16 atom. So that's the MCG, and to give you a feel for size, that's 10 to the minus 10 of a metre, 1/10,000th of a millionth of a metre. That's it in metres. That's pretty tiny. It's very different to biological objects, remember the scale, very different to chemistry, very different to geology and earth sciences. Now, let's build oxygen-16. So we grab 8 protons. They're positively charged. Think of magnets, north poles, they hate each other, they want to repel. And you're going to try to shove those all the way into the middle there. And by the way, to give you a feel for size, remember the MCG is the atom, and you've got jelly beans. 8 red jelly beans, and you've gone and put them in the middle of the MCG. I don't think you can see them. And then they want to fly apart, and so you grab 8 neutrons, neutral particles, and apparently when you push them in together, that magically becomes stable. And remember, there's 8 positive charges there, and so now you grab 8 electrons, and they're tiny. Where are they? You grab 8 electrons, they're tiny. I can't see them. They're tiny little specks of dust somewhere in the outer, and that's the physics model of the atom. And what's in between? What else is there? There's nothing. Actually, we say it's a field, footy field or electric fields, yeah. Very bad dad joke there. 3 people laugh. Anyway, so that's the model of the atom, and this is the type of physics that I learned. This is how useful I was to society, and this is apparently got nothing to do with the moon. All right, anyway, so how do we make water now? This is nuclear physics 101. Actually, it's not really. It's really sort of electrochemistry 101. You grab an oxygen. By the way, there's the oxygen. Niels Bohr worked out apparently there's 2 inner electrons in a closed shell, and there's 6 electrons in the outer shell. There's 2 holes there. They're the 2 holes, room for 2 more electrons. And you grab some hydrogen, and you actually beautifully bond that into there and you make water. And oh, by the way, you just need a little bit of energy. Does hydrogen go boom? I was going to insult you by putting, some sort of airship photo and having it explode. We're not allowed to do explosions, but if you really beg us later on, we'll do an explosion in the corner there and see whether we can trip the fire alarms in this theatre. We'll just do it towards the end so that you can do a safe exit should we actually do anything wrong. And if anything does go wrong, Tony Klein in the front office is the safety officer. So if you see him running, try to keep up. All right. So finally, what about breathing? Hey, I thought this was a physics lecture. So far I've talked about a little bit of nuclear physics. Well, what do we know about breathing? Well, here's all I know about breathing. That we breathe oxygen, and it's the third most abundant element in the world, in the universe, but there's none of it around. It came as a surprise to me because I looked at this and we've got technology here. Steve's I brought an oxygen meter. Actually, here's somebody, I'll just breathe in, so, hang on. That's okay, Steve, this person I trust here, what does that say? 20.9, so the ambient air in here has got 21% oxygen. And here's what I found out, I had no idea, that apparently when the Earth was formed 3 billion years ago, despite it being good enough, to actually almost support life, there was no oxygen in the atmosphere because most of the primordial oxygen had leaked away, through the polar caps and everything else like that. We could come up with this thing that gravity keeps our atmosphere around there, but most of the oxygen had either leaked away or been used up, in all the chemical processes, because oxygen is one of the most highly reactive elements that we know of. And then all of a sudden, 2.7 billion years ago, a little bit of evolution kicks in and magically it becomes 20.9. So I went to a lot of trouble, at least 2 hours of e-searching on Google before coming here tonight to try to work out why it's 20.9. And the answer is, we don't really know. One of the most fundamental things on this earth, and we're all worried about breathing, and we have no idea why it's 20.9 and how long it'll be 20.94. But we can rest assured, as the earth has cooled and the oceans have formed, we've got an oxygen to breathe, and we now actually can breathe. Where does it come from? Well, it comes apparently some from trees, but do you remember what covers most of the earth?
What's that?
Oceans. Right? And they have tides and all those types of things. And here's what really happens is that more than 70% of the atmospheric oxygen that we breathe comes from the ocean and from plankton and from algae and blue green algae and is it cyanobacteria? I had to learn how to say that. I didn't know. I'm a physicist. Hydrogen and helium was my limit. And this apparently is what it looks like. And apparently it's really healthy for you. I also brought some more health food, which I'll show you later on. I brought a sandwich box of some other health food, which we'll talk about. And these people are so excited by this algae that they feel it gives you medicinal properties to bathe in it. Thoroughly recommend it to somebody else, not for me. The tides. So in preparing this, apparently you had a perfect lecture on tides last week, on the moon tides and everything else like that. So I don't need to go to it. But a simple question you could have asked any physicist is, how long is the lunar month? And they would have told you, I don't know, 29.263 days or whatever it is exactly. Well, one person in this room spent an important part of his young life measuring this and came up with the fact that apparently it's changed over the last few years. And so although it is 29 point something days right now, it's actually been changing. And by the way, that's today at this end, and that's yesterday in this direction. Now, somebody said, before whatever it is, BC, we say before computers actually nowadays, and after AD's after digital, right? Together, so that's our nomenclature. And so here's what's been going on, and it's been changing. So this world of physics that we think everything is constant is constantly changing. It's just on a very different time base. And so finally, I have the complete wrong story to put together. And so here is creation 101 according to Roger. This is the start. This is how you build the universe. This is oxygen, the moon, and what else? Physics. Yeah, that's right. Oxygen, the moon, and physics together. So the air we breathe comes from the oceans. The life in the oceans depend on the tides, and the tides are affected by the moon. Right? So that's it. That's a very straightforward lecture. And so you start with the Big Bang, and you do all this in between, and you finally get life. And it's really, really straightforward. And you don't need to study anymore because that's the end. Well, of course, it never is the end. So imagine we did go to the moon. And we've already worked out that the moon appears to have no atmosphere. Now, the physicists can actually tell you it has no atmosphere because we can look with a telescope and try to sort of see, like look at starlight through the moon and try to study it. Dave knows we can now send objects on. Dave was in love with the rovers, one of them. They've finally all given up, haven't they? Yeah. And we can send devices that crawl across the moon, and there are people who argue that there is some atmosphere, levitating dust and all that type of stuff. There are people who argue that it had an atmosphere at some point or whatever, but the reality is if we're going there, you're not going to breathe. So as far as I'm concerned, no matter what esoteric argument we have about there being, some sort of water or oxygen on the moon, it ain't there for me in big properties. Now the key breathing facts, I had to remind myself, apparently we breathe to stay alive, right? So having got that, I didn't know, I thought it was about 2 litres. I was surprised adult lungs are 3 litres. I didn't know that. I'm a physicist, we don't deal with human bodies too much. And this is what really surprised me, because having got a device to measure the amount of oxygen, I'd always known as a kid, you breathe in 21% and you breathe out 16 or 17%. I always knew that. So I tried to measure it, and I couldn't. And then I started to look into it. And it's because the gas exchange that occurs in your body is typically a small percentage of all the gas that's in your body. Anyway, to cut a long story short, to breathe every day, you need about 500 litres of oxygen. Now, this is not 500 litres of oxygen. This is probably, what do you reckon, 300 mils or something, or thereabouts. David, if I were to guess, what volume would you reckon that is, brother? Yeah. Typical bloody physicists, because we're going to approximate this to apparently 1 metre by 1 metre by 1 metre. It's not. It's about 374 litres, which I was going to approximate to 500 litres. And so in here, I have enough oxygen to keep me alive for 1 day. So next time I go to the moon, I'm taking my model of the moon with me to breathe. And by the way, the density of water is, 1 kilogram per litre, or 1,000 kilograms per cubic metre, and the density of air is 1.2 kilograms per cubic metre, about 1 kilogram per cubic metre. So if this is about half a cubic metre, this is about half a kilogram of oxygen or air in there. It happens that oxygen and nitrogen are roughly the same way. Okay. The other thing I didn't know is that your breathing cycle is dependent on carbon dioxide more than anything else. I mean, I'm a silly physicist, but apparently I could work out how to make a proton and a neutron or whatever, but I couldn't work that out. So, if we breathe 8 litres per minute, that's 11,000 litres in a day. If you take in air at 21% oxygen and you use up 5 percentage points of that, you can do the numbers and crunch and come up with that 500 litres. That is enough to keep you alive if you had some magic way of just putting oxygen into your body. That's not what we do, by the way, because we breathe a lot of air to actually get some oxygen and weigh some oxygen in front of us, but it's nice to know. So when the Apollo spacecraft went to the moon, they had to carry all the oxygen with them. Now they thought long and hard about whether they would have an atmosphere of air in that cockpit or in the capsule itself. And this comes as a surprise to everyone that despite the major fire that they had, and I can explain the fire later on in questions, they went with 100% oxygen atmosphere to the moon, Apollos X to Y up to 17. I think they might have changed after 14. And 100% oxygen atmosphere. Isn't oxygen dangerous? Yeah. See, I think it's really dangerous. It's very, very, how would I say, very bad of them to do that. Yeah. Anyway. And then, of course, they developed technology. People have said, what did the space program ever do for us? Well, develop life support systems. This is the approximate circuit diagram for this device that these astronauts wore out in the middle of nowhere. I want you to imagine that you're out physically in nowhere where there is no water, there is no oxygen, there is no atmosphere, and you have to stay alive. And it's all good and proper to say, oh, I've got an oxygen tank like my barbecue gas cylinder. I'll just run down to CIG and top it up and then just bring it back. They couldn't do that. And the technology that took people to the moon, that calculated the kinematics, calculated the trajectory and all that, was the physics, the engineering, the geophysics, the biophysics, the chemistry, the biology, the psychology, everything else. All the sciences coming together to do the impossible. That was a long time ago. And as I said, that was my dream. I was going to be an astronaut. And yeah, that dream doesn't always come true. Got time for a couple of, no, I'll do the twist and then Steve.
Yep.
Can we do a couple of the demos? Would you guys like waking up or not? Yes. Yeah, that was very quick. It was, yeah. Actually, you're very lucky. I'm not calling for volunteers. I normally call for volunteers, but this one's rather dangerous. So I said to Steve, I think it's really important that we look at oxygen. Actually, let's do this one first. So we're not allowed to light fires in this theatre anymore, so you're not allowed matches. So this is not a match, so that's not what you're seeing, right? And this is not a candle. Whoops. We're meant to use LED candles now, Steve, from now on. Yeah. Steve, you're not listening. So can you just pretend this is an LED candle? And here's another LED candle. Okay, all right. So I'm going to simulate this candle being, there's a candle, I'll put this one out of the way, and here's a simulation of a candle burning on the moon in 5 seconds. The simulation begins in 5 seconds. 4, 3, 2, 1. That's what the candle will look like when you set fire to it on the moon. All right, do you agree? Oh, it's pretty obvious. I mean, I just couldn't work out how to remove the atmosphere, so I used up all the oxygen. Okay, so let's go back to here. So here's candle 1, candle 2. By the way, these are 0.134 watt candles, or 1 candela, right? Yeah, that's the output, the light output. And okay, so do you see that these are identical? I can swap these back and forth. Here's a little device here, by the way, I've just had running. This is a little 302 device that I'll just put this little device in it here, and I'm just going to change the atmosphere of this little world ever so slightly. And so that device is running there, and we're going to do that experiment. This device is over here. I'll breathe in as well, right? And then I'm going to do no tricks of the trade. Here we go, and just watch very carefully. Are they the same brightness, by the way? It's within 1 or 10%. Is this one brighter or that one? Which is brighter? This one. That one? This one's a brighter one. Cool. Even better. Okay, here we go. Hope this works, Damage. Yeah, we're good. Whoops. Sorry. This is, I never do these things live. Always record them. They're always much better when you record them. All right, I think this is good. Let's go and a little bit longer. Yeah, not quite that difficult. Oh, thought I was going to get it. And now all I'm going to do is I'm going to change, whoops. Luckily we're not allowed to use matches, Steve. Did you bring another box in case? Or? No one smokes anymore, so Max and Tony used to smoke in lectures. You're not allowed to do that anymore, are you, Tony? Alright. I'm telling all these tales that we're not allowed to say. Alright, so all I'm going to do is up this ever so slightly, and I can hear it now. So I'm increasing the oxygen content in this area here compared to this one here. And we're going to go again. And then of course, yeah, it lasts 10 times longer. All right, so somehow this makes candles last longer. So that's, or burn longer, anyway. All right, so Steve prepared, Steve, can we fill a balloon with this stuff, do you reckon? Whoa, yep, okay, somebody's warning me. That's one of their systems. So here we go. I'll just fill this. Is oxygen dangerous, by the way? This is an oxygen machine. Ah, do you want me to measure the concentration? Who was asking me for the concentration? I'll tell you what the concentration is on this meter in a minute. You'll be the person to read it, okay? Let me just... this is the classic where... there we go. There we go. It's actually finally blowing up. There we go. Is this increasing the concentration or the pressure? The pressure's on. This thing's warning me right now. All right, and so this could be dangerous or not dangerous. The lady said only in high concentration. What will you define high?
Not that. Much high.
Oh, you mean higher pressure or higher concentration?
Concentration.
Okay, well let's just check. So it's reading, here we go, 20.9, and let's just check what this machine is generating, and you'll see whether this person is happy or not happy with it. I mean, all right, do you want to tell her whether she should worry about this? Last time I looked, this thing is saying 50, 60, 70, 80, 84%. Is that bad or good? Is that pure oxygen?
Not pure.
No, pretty good. All right, so let's just check. And Steve set up a camera over here. Steve, can we go to this camera or not?
Yeah.
Oh, so Steve's getting worried. Okay, so let's check. What would happen if I set fire to this? Okay, well, let's have a look. All right, so Steve, so we're forever. Oh gosh, Steve, you've got the knife loose there. All right, so here we go. So here's our oxygen balloon. Steve's got the technology that apparently we're live. Steve, we're not live here, I don't think yet. We're still on still frame there. I'll take care of that one. Yeah, right. Yeah. Because people often worry about oxygen being explosive. Yeah, there we go. All right, so that's it. So yeah, we're live in the camera there. Very good. You good to go or not?
Yeah, I can share that. Picture's bigger though.
Well, we'll roll with it as it is. Yeah. That's what life is. We're recording. You triggered?
Yeah, it's triggered, yeah.
You okay?
Yep.
Ready? If Ryan's got a balloon phobia, now's the time not to worry about it. Well, yeah. And that was just such a non-event. I mean, Steve, I just said that was such a non-event. I mean, here's another balloon that I filled a little bit earlier. This is another balloon, and it's not helium because it doesn't float. And in fact, it's just from this type of oxygen gas that we actually set up before, liquid petroleum gas. And let's just have a look. Same experiment again. Identical conditions. Did you rewind it, Steve? Did it? Nothing? Don't worry about getting it bigger. See how we roll. This is the whole thing about doing demos, and this is what I always say. The demos always come to bite you in these lectures. Any luck, Steve, or not?
No.
All right. Maybe Steve will get on the still frame. Do I do it with the candle or with the match? Did you put air in it or not?
Just a little bit.
Alright. Alright. Oops, sorry. Alright. Is it going to work, Steve?
Yeah, it's going to work.
Alright, here we go. Oh, Steve, just...
I've got another one.
We practiced all afternoon with this, and we had one where the flame went up this big. Has that got gas in it or not?
I'll put my bucket in one.
Let's make it one. Yeah, alright, okay. So, right. This is the problem with all these safety regulators we've got nowadays, Steve. I mean, why don't you just hold this here for about an hour, Steve? Then yeah. You sure? All right. All right. All right, Steve. I trust you. The candle's there. Yeah. Well, actually, I'll just get you to hold that if you like. Oh no, that's yeah. We go to all this trouble. We're trying to prove to you that oxygen is not dangerous. And the only way of doing it is to prove that something else is. I suppose this is not exactly the safest way of doing that. Yeah. And that's it. It's sort of holding there, Steve. It's not exactly tied. Are you ready? Do you think this is going to work this time, Stephen? You sure? Still frame this and play it back at really slow. There we go. Yeah. All right. Thank you, Steve. That was so exciting. I've lost the remote control unit for the lecture somewhere. Yeah. It'll turn up somewhere. Here it is over here. Whoa. We good? I'm just going to take it to you. All right. So that wasn't going to happen, that dream wasn't going to happen. Instead, I had to work at all these places that David said. Got to work hard with students in my group, and that's how we slummed it. My parents have always wondered whether I had a real job. We worked on some of the biggest experiments, the Large Hadron Collider. We built the detector systems for that. Got to show, well, I'm very good at actually getting rid of deputy prime ministers, so we're not going to show the ground. The dreams come true. We found the heats, we built the Australian synchrotron, and then something happens, the clock turns back, and the clock's reminding me that I've got 5 minutes. And there's a big change. Here's the 30-second summary after all this time in physics. And this became a real change in our lives. We went along for the first time and we found out from our colleagues about the plight of pneumonia with young children. And remember, pneumonia is an illness where lungs become infected and children can't breathe, or adults can't breathe, people can't breathe. And this surprised me that 80% of these young children would never reach hospital. And that 1 every 30 seconds was dying. A good friend of ours, Jeff Opad, taught us years ago, there's pi by 10 to the 7 seconds in a year. And it's terrible to be able to apply that statistic and therefore work out that if there's 1 million or so dying, it's every 30 seconds. And we felt that we had to act. Here's the 30-second summary. 1.6 billion people on Earth have got no electricity. They've got no access to food or water and stuff like that. When their children get sick, they don't have anything. And oxygen's a life-saving illness. Here's what kills kids. This is what kills under fires. People think it's AIDS and malaria and car crashes. It's pneumonia and diarrhea that kill these kids. And most of these children die in these very low resource settings of the world, not where we live. Where I did all these experiments were in Australia and in the US and in Sweden and in the UK. All of these places that are green, they're the safe places to live. These are not the safe places to live. I took these photographs when I had some time in Nairobi. This is actually in Kibera, in one of the slums in Nairobi. And this is where people get their water from. It was just disheartening. We ended up working in Uganda. Uganda has a population of 40 million people. 40 million people. It's got 2 main hospitals and 14 small district hospitals. That's it for 40 million people. The reality is, that's not where the problems are. This is not where we're going to go. And this is a quick plug for the 302 project. We're going to these thousands of the smaller clinics where the mortality is, where the children are dying. And this is what a typical hospital ward in an African hospital looks like. It's got nothing. It doesn't have this beautiful projection technology, whatever, it's just got a wall. And these are the solutions that people have, but they don't work. You know, we're working with these small oxygen concentrators, and I'm going to explain to you the basic physics or the chemistry on how that works. Take electricity, compress air, make oxygen. Or take a lot of electricity, cool air, extract oxygen from the air. Do you get me? That's how we make oxygen. We don't create oxygen. We just grab air and we separate oxygen from the air. And none of these work. Now, there was this useless guy called Baton Picard and his mate who were going to create a solar aeroplane and fly all over the world. Everyone kept saying to them, hey, what use is that? You're never going to carry passengers in that. It'll be of no use whatsoever. And instead, oh no, we want to change thinking. People say you can't fly around the Earth without using fossil fuels like you saw. And they said, no, we can. And they proved that we can. So our team set up to achieve the impossible. So we said, let's actually concentrate oxygen using no electricity. And it was a very, very simple plan that we would use running water. And Steve set up a beautiful demo here. Maybe I'll get to show it right at the end, where we've got some running water. And we take water from a river and we siphon out of the river. Oh, Steve's got the siphon running there. Might as well do it, Steve. You went to all trying to set it up. So let me just get our siphon running. I don't think we need a camera. There we go. The river's working. Now there's an amazing property of a siphon that people don't know. So everyone's siphoned fuel out, so everyone knows how to do this, is that right? Yeah. Now, we actually came up with this other idea that we could climb a tree and put our siphon up in this tree, and we imagine the tree's up there. I haven't got time to do that tree. And the siphon keeps flowing. It's a beautiful thing. And then because we're physicists, we knew at the top of that siphon we could put a hole in the siphon and the water wouldn't come out, air would go in, and we would get a vacuum. So out in the middle of nowhere, we could get a vacuum. And a vacuum's a bit like a pressure, just the physicists ran the wrong way. And we turned that vacuum into a source of energy that would suck air through this very simple compound called a zeolite that we didn't invent, the chemists invent, and that traps nitrogen, and we'd be left with oxygen. And that was our idea, very simple idea.
Pneumonia kills more children globally than any other disease. Reliable oxygen supplies could save countless lives, but that needs a reliable power supply, often lacking where it's most needed. Now, a small team has tapped into a simpler power source, the water flowing in a stream. Their ingenious system compresses air, then filters out the nitrogen to produce life-saving oxygen. They call it free O2. Low cost, easy to maintain, just add water.
And then, since then, Free O2 was born. It's a physics project, but it's interdisciplinary. We now have systems running primarily in Uganda and Tanzania. We have some systems now in Nigeria, and we're sending systems to Timor-Leste and the Solomon Islands. They're not all based on the water system. Because when we have the water system, people say to you, hey, what would you guys do if there's no water? And we say, we'll build a solar system. And then people say, what do you do when it rains? We say, we use the water system. What do you do when you have electricity? We just decided the problem was to get rid of these things and solve the oxygen problem. And the problem was more than just innovation. So free O2 stands for fully renewable energy oxygen. Free O2, give away the oxygen. And we built technology, we built a social enterprise, and we built partnerships. The university's been phenomenal. It's allowed us to get away with blue murder. Do what you want to do, get paid to do it, and love what you're doing. And we're now starting to employ people. This is Frank, our lead oxygen technician. He's a plumber, by the way. Notice I call him the lead oxygen technician, a plumber. And Frank's job is to manage our systems. And our systems take these blank walls and put a FreeO2 outlet on that blank wall with a constant, reliable source of energy, oxygen. Not reliant on reliable energy, but the oxygen is reliable. We go to a lot of trouble to use our physics knowledge, our engineering friends' knowledge, our economists' friends, and everyone else to develop a reliable source of energy, oxygen. And how we do it is to be agnostic of the energy. We don't care where the energy comes from, we can use it. We're the ones who said we can do it with no electricity. Believe it or not, we can do it with electricity pretty well. And we can store the oxygen. We store it, by the way, in these amazing big bladders. And everyone keeps saying, this, oh my gosh, that's dangerous, you know, so we had to set fire to a few to just show them that we couldn't burn it, you know. And so there's all the technology, but the most important thing is we put a brick wall between the technology, because we want the health workers in our installations to focus on the health. It's in particular the children that they're delivering. And so it's basically a team job. Here's our team, just quickly. This was our engineering team from last year. They won the top Endeavour project, plus they won the social media project. They didn't like winning the top mechanical engineering project because that came with no money. The social media one came with $2,000 or something like that. So they found that was much better. We won the World Pneumonia Day, we won the Fisheries thing, we won the Eureka Prize, and everyone suddenly started realising that this was serious. A bunch of physicists on this journey with this nutcase idea 8 or 9 years ago that we would produce oxygen, and we've basically gone through, and after 7 years of R&D work, on July 17th, whatever it was last year, we treated our first child, baby Francis. Can you imagine, for 7 years, people saying, hey, what are you doing? So we're trying to make oxygen, they just buy it. How many children have you treated? None, 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 none. We're so proud now, that answer is no longer 0. That wall has actually got FreeO2 on the back of it. And this is a shameless plug for the great work. That's the oxygen bags that we store the oxygen in. There's 100 or a few hundred people who go home tonight saying it's safe. I saw you set fire to it. Oxygen systems. By the way, all of the data acquisition systems, all of our technology from CERN and the Australian synchrotron, we've actually got in these systems. I could dial in right now and tell you how much oxygen it's making. This was what Francis looked like when he turned up, really, really sick. And 2 days of oxygen, and this was Francis. Right? We're very lucky with Francis. You know, Francis might have died, true. But 2 days of oxygen, and this child, I got to hold this child. This is Carly Silva. Brent and I and the team, we pitched to her in 2013 the nutcase idea of doing it with no electricity. I'm not allowed to say this anymore, but I will say this to the audience. We're so proud of ourselves. We were going to do it in 6 months. You know, we wrote the thing, we're going to do it in 6 months, it took us 6 years, you know. We're dealing with the merchant bank right now, and we're not allowed to say that we're going to take 6 years to do anything. This is the future of FreeO2. This is FreeO2 Uganda, that's a team, and here are their stats so far. So you see the zeros, children treated, and all of a sudden now we're up to 282, and we're going to be climbing there. And it's all about Francis. So thank you for listening tonight.